Questions 21 through 25 on the 2017 Grade 12 AMC 12A. A set S is constructed as follows. To begin, S equals 0 and 10. Repeatedly as long as possible if x is an integer root of some polynomial for some n greater than or equal to 1, all of whose coefficients ai are elements of S, then x is put into S. When no more elements can be added to S, how many elements does S have? In this question, we're going to use something called the rational root theorem. And the rational root theorem states that if you have any polynomial, the possible rational roots are as follows. The factors of the constant divided by the factors of the lead coefficient. So let's give an example. Let's say we have a polynomial 6x to the power of 3 plus 8x squared minus 7x minus 3. And I said, what are the possible rational roots? Well, you would say that I would get the factors of the constant. So the constant is minus 3. So the possible factors are plus or minus 1 and plus or minus 3. So that would be what would go in the numerator. And then the factors of the lead coefficient here is 6. The factors of 6 are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So for each of these, you would get a fraction, and that would be a possible rational root. So for example, if I took 1 and negative 3, 1 as the numerator and negative 3 as the denominator, that's one such possible rational root. So now what we have to do is use the same thing for our question up here. Now our question can be looked at in the exact same way. So we want the possible rational roots. And how do we get that? Well, use this formula. So we want the most, judging by the wording of the question, when no more elements can be added. So they've added the maximum. So in order to get the maximum, I want this scenario to generate the maximum number of fractions. And the way I can do that is as follows. We first will have to create some sort of polynomial, right? We are given this big long polynomial, but we have to create one, and we don't have much of a choice. We only have 0 and 10. So I'm going to use 10, and I use a simple one, 10x plus 10. And 10x plus 10, that will be my polynomial, and they are saying that x is an integer root of that. So if this is set to 0, the root is obviously negative 1. So that means that my set now has become negative 1, 0, and 10. Before it was 0 and 10. Now that root is added to the set according to the rules of the question. But I don't want to keep going like this because that's going to take forever. So I want to now use this rational root theorem. Okay, when I use the rational root theorem, I want the maximum number, so I think I can get it as follows. The factors of the constant. Okay, I am going to make the constant 10. I don't have much of a selection. I want to make it the maximum. I don't think I'll be able to make it a maximum if the constant is 0 or negative 1. So I'm confident that if the constant is 10, it will give you the maximum number of rational roots. And then I'll skip ahead to the lead coefficient. The lead coefficient, whatever it is, x to the n, that lead coefficient I will choose, well, I've got a choice here. I can either put negative 1 or 10. I'm going to choose negative 1, and let's see what happens. So using the possible rational roots equation, the factors of the constant are going to be plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. And the factors of the lead coefficient, just plus or minus 1. And this gives me 8 values. So those 8 values, those are basically the roots, will go into my s. So my s now becomes plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10, and don't forget these guys. Well, the negative 1 I've already put in, the 0 I haven't, and the 10 I've already put in. So this s has now 9 values, and that is the maximum. So number 21, the answer is D. A square is drawn in the Cartesian coordinate planes with vertices as follows. A particle starts at the origin. Every second it moves with equal probability to one of the 8 lattice points closest to its current position, independently of its previous moves. In other words, the probability is 1/8 that the particle will move from xy to each of the 8 lattice points. The particle will eventually hit the square for the first time either at one of the 4 corners of the square or at one of the 12 lattice points in the interior of one of the sides of the square. The probability that it will hit a corner rather than an interior point of a side is m over n, where m and n are relatively prime positive integers. What is m plus n? All right. Okay, let's, in a very non-scientific way, first let's just look at this diagram, right? So we've got 2, 2, and all that stuff. And we don't need to label the diagram in terms of its coordinates, but I do need for you to understand that we've got a lot of points in here, and I'm going to just draw them, these little lines here to indicate what points I'm talking about. Now we are starting at the origin, which is of course right here. Now let's going to talk about 2 or 3 rather probabilities. Probability of a corner, probability of an edge, and the probability of O, which is origin. And let me explain what each of these means. The first one is the probability of getting to a corner from the inside corner. So what that means is the probability of getting here from an inside corner, and that inside corner is there. What's one example? So for example, 1, 1 is such inside corner right here. This would be 1, 1. PE is the probability of getting to a corner from an inside edge. So for example, one such inside edge is 1, 0, and that is 1, 0 is right here. So the probability of getting to a corner from here. And then P0 is the probability of getting to the corner from the origin. And that is really what we're interested in. That is basically what the question is asking, find P0. So here's the origin and here's the corner. All right, let's talk about this now. We're starting at initially an inside corner for PC, right? So let's talk about PC first. PC is as follows. To get to an inside edge, the probability would be 2 over 8 to get to an inside edge. And let me explain that first. So we are starting at an inside corner. We're starting here, right? And the probability of getting to an inside edge, this is an inside edge, and this is an inside edge. As you can see, there's a probability of 1/8 of going there and a probability of 1/8 going there. So you have to add them. That's why it's 2 over 8. Okay, so that takes care of that. Then, if we're starting at an inside corner, we also have to talk about the probability of getting to the origin. Well, to go from here to here, there's only one route, and that route has a probability of 1/8. So that's pretty straightforward, 1 over 8, PO. And then we have to talk about the probability of getting to the outside edge and stopping. So we're starting here, right? Starting at a corner. If we get to this outside edge, either here, 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 or here, well, it's game over. We've sort of lost because we're trying to get to a corner. So that basically represents a probability of 0. So we are really going to put 4 out of 8 times 0. And then finally, when we start at the outside corner, the probability of getting to that corner that we are trying to get to, and obviously there's just only one way, and each move has a probability of 1 over 8. And there we go. So this would be PE over 4 plus PO over 8 plus 1 over 8. And then we got to go through the same sort of conversation again, but this time when we are starting at the inside edge. And the inside edge, of course, now we're trying to figure out PE. From PE to get to an inside edge, so we're starting at an inside edge, and if we want to get to an inside edge, we can go either here or we can either go here. So it looks like two paths. Each path has a probability of 1 over 8, so we add them and we get 2 over 8. And then we want to go to, say, a corner. From here, we can go either here or we can either go here. And that obviously is also 2 over 8. 2 over 8 PC. And then from an inside edge, if we want to go to the middle, which is here, the origin basically, that will be just 1 over 8. So 1 over 8 P0. And then from the inside edge, we can go to the outside edges, either here, here, or here. A 1/8 probability, 1/8 probability, 1/8 probability, so 3/8 probability. But when we get to that, that's a probability of 0 because we're not interested in that. We're only interested in getting to the corners. So we don't count those. So this in lowest terms is PE over 4 plus PC over 4 plus looks like PO over 8. And then we have one last one, start at the origin. And when we start at the origin, that will be PO. We're starting here now. From there, we can either go to the edge, either here, 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 or here. So there's obviously 4 ways. Each has a probability of 1/8. So you add 1/8 to each, to 1/8 4 times. So it'd be 4 over 8. And that's probability of E. Or you can go from the origin to the corners with the same probability, 1/8 times 4, which is 4 over 8. And this one gives you PE over 2 plus PO over 2. All right, so we've got 1, 2, 3. 3 equations and 3 variables. And you solve those, and I'll let you do that. So I'll let you do that mathematics, and when you do, you get 4 over 35 for PO. PE becomes 1 over 14, and PC is 11 over 70. What we're interested in is PO. That was what was equivalent to M over N, and M plus N, therefore, will be 4 plus 35, which is 39. 39 is the answer to this question, and therefore, number 22 is E. For certain real numbers a, b, and c, the polynomial g at x is equal to x to the power of 3 plus ax squared plus x plus 10 has 3 distinct roots, and each root of g at x is also a root of the polynomial f at x is equal to x to the power of 4 plus x to the power of 3 plus bx squared plus 100x plus c. What is f at 1? All right, so we have g at x is equal to x to the power of 3 plus ax squared plus x plus 10. And we can factor it calling those roots r1, r2, and r3 like that. And then they also told me that f at x, which has been given, has 4 roots, but 3 of them are the same as the roots for g at x. So put those same 3, and then we'll add 1/4 root and call it R4. All right, and now we can proceed. Now, what I'm going to do at this point is, instead of these 3, I'm just going to put in this guy since it's equivalent. So that would be x to the power 3 plus ax squared plus x plus 10. And then we've got that x minus r4. Now I'm going to expand it. And when I do, I get the following. X to the power 4 minus r to the power 4x cubed plus ax cubed minus ar4x squared plus x squared minus r4x plus 10x minus r4 10 times 10. Now, of course, I'd like to collect like terms. So x to the power of 4, and then let's see what I get for x to the power of 3, that coefficient, minus r4 and a. So a minus r4. And then x to the power of 2, what's that coefficient going to be? Minus a r4 and then 1, it seems like. Okay. And then for x, looks like 10 minus r4. And then I've just got this 10r4 as the final constant. Now at this point, we have to compare. So we have to compare now this equation right here with this equation, since they both represent f at x. And this is f at x. Okay, so let's look at this one first. The fact that this coefficient is 100 and this coefficient is 10 minus r4. Those are equivalent. So 10 minus r4 is equal to 100 since they represent the same coefficient. So that means that r4 is negative 90. All right, let's do another one. Let's see what I can do. This one, a minus r4 is equivalent to this coefficient, which is just 1. So a minus r4 is equal to 1. That means a is equal to 1 plus r4. R4 is negative 90, so this is negative 89. Okay, so I think that should be enough to figure out f at 1, which is what we have to figure out, right? F at 1 is what we are trying to figure out. Okay, I think we have all that we need. And in order to figure out f at 1, I will use this form right here. So here we go. F at 1 is 1 to the power of 3 plus a, which is negative 89, times x to the power of 2 plus x plus 10. And then all of that multiplied by x, which is 1, minus r4, so plus 90. Yeah, all numbers. So this is 1 minus 89 plus 11 times 91. And that looks like what? 89 plus 12, minus 89 plus 12. So that's negative 77 times 91. And that is minus 7007. So f at 1 is minus 7007, and that is choice C for number 23. Quadrilateral ABCD is inscribed in circle O and has sides AB is equal to 3, BC 2, CD 6, and DA 8. Let x and y be points on BD such that dx over BD is equal to 1 over 4 and by over BD is equal to 11 over 36. Let E be the intersection of line AX and the line through Y parallel to AD. Let F be the intersection of line CX and the line through E parallel to AC. Let G be the point on circle O other than C that lies on CX. What is XF times XG? This is the diagram of this question, and here we go. The first thing is, of course, we've got some similar triangle situations, and in particular XEY, that triangle, is similar to triangle XAD. And from that, we get that XY over XE is equal to XD over XA. We have another similar triangle situation, and that is triangle XEF is similar to triangle XAC. From that, we get that XF over XE is the same as XC over XA. And now what we have to do is we've got to fiddle around with this to come up with a logical sort of conclusion. Both of these have XA in them, so we can isolate for XA pretty easily. It's going to be XE times XD over XY here. And then from this guy, it'll be XA is equal to XC times XE over XF. And then we can set these equal to each other. XE, XD over XY is equal to XC, XE over XF. And then the XE's cancel, so you're just left with XD over XY is equal to XC over XF. Now we get to something called the power of point theorem. And some of you may remember this, some of you may not. It basically states that if you have a circle and you've got two lines, let's say, there's some variations of this theorem, but I'll just give you the variation that we are going to use. And let's say you label it A, B, C, D, and E like that. The power of point theorem states, in this particular diagram, it would be AE times CE is equal to BE times DE. So that's what we have to use on our diagram over here. We have to use the power of point theorem. And when we do, we get the following from these lines. I'll draw them out for you. The line from G to C goes through X, that one, and the line from D to B that goes through X right there. As you can see, that's similar to what's being shown here, so we're going to use the power of point theorem on that. When we do, we get the following, that XC times XG is equal to XD times XB. So that is what we get from this power of point theorem on our diagram. Now we can manipulate this a little bit because XG we can put over here and we can put below it XB, and then over there we can put the XD and then put below it XC like that. And the reason we want to do that is because when we do that, we can kind of get it into a form that this could be manipulated into, right? Because that one could be changed into the following. It could also be written as XD over XC, and the other side would become XY over XF, like that. So now we've got XD over XC equal to this, but we also have XD over XC equal to that, so that means those two are equal to each other. So that means that we conclude that XY over XF is equal to XG over XB, like that. And if you cross multiply this, you get XG times XF is equal to XB times XY. Well, this is very good news because XG times XF is exactly what they want me to figure out. So we are headed down the right path here. Now, I want to keep this diagram in the photo, so I will. And let's just bring that finding over here, that XF times XG was equal to XB times XY. Now we have to use some of the information they gave us in the question. The question, they told us the following, that BD is 4 times dx. So, for example, BD from here to here is 4 times dx. That was told to us in the question stem. So I'm just going to call it d, and therefore dx I can call d over 4. I'm just going to use d as sort of a variable. They also told me a relationship between by and bd. They told me that by is 11 over 36 bd. So I can write by is 11 over 36 times d. All right, I think we are ready to tackle this now. Remember, this is what we're trying to figure out the value of. Okay, so this will give me, I have to write this out. xb is actually bd minus dx, if we looked at that diagram. xy is actually bd minus dx minus by. And now I can use my variable. bd is d, dx is d over 4. bd is d, dx is d over 4, and by is 11 over 36 d. So this is 3/4 d, and this becomes 4 over 9 when you do the math, d. So when it's all said and done, this is d squared over 3. So this is d squared over 3, but the answer choices are all in numbers. So I've got to figure out, obviously, the value of d. The value of d I can figure out using the cosine law. So the cosine law will be used, but also another fact that they told you in the question, that this is a cyclic quadrilateral. And you know that because it's inscribed inside a circle. This quadrilateral is inscribed inside a circle, so therefore it's cyclic. So a fundamental property of cyclic quadrilaterals is that opposite angles add up to 180. So angle BAD, if that's, say, theta, then the opposite angle, which is DCB, will be 180 minus theta. So here we go. Let's use the cosine law now. The cos of theta, I'll just go straight to isolating for it, is AB squared plus AD squared minus BD squared over 2 times AB times AD. And then we have all these numbers. It's 3 squared plus 8 squared minus, well, BD is D squared. That's the only one we don't have. And then this is going to be 3 times 8. So this is going to be 73 minus D squared over 48. Now we do the same kind of thing, but this time for cos of 180 minus theta, which is the opposite angle. But cos of 180 minus theta is negative cos of theta. So that's why the cyclic quadrilateral aspect or fact really helps us. Again, I'm just going to do the isolated portion of the cosine law. So CB squared plus CD squared minus BD squared all over 2 times CB times CD. And we know these numbers. These numbers are 2 squared plus 6 squared minus D squared over 2 times 2 times 6. And that would be 40 minus D squared over 24. Okay, so cos theta equals this, minus cos theta equals that. We can set them equal. We just have to reverse one negative sign. So this will be D squared minus 40 over 24, like that. When you solve for D squared, you get D squared equal to 51. And therefore this D squared over 2, or 3 I should say, is 51 over 3, and that's 17. And that was equal to this XF times XG. XF times XG. And that was what they wanted us to figure out. XF times XG is 17. Therefore, number 24, the answer is A. The vertices V of a centrally symmetric hexagon in the complex plane are given by these points. For each j between 1 and 12 inclusive, an element zj is chosen from V at random, independently of the other choices. Let P be the product from j from 1 to 12 of zj. Be the product of the 12 numbers selected. What is the probability that P is equal to -1? Well, zj can be any one of these 6. 1, 2, 3, 4, 5, 6. And we can choose any one of those for zj. All right. Well, some of these are similar, so I'm going to put them in two different groups. I'm going to put this and this together, and then the other one I will put in a different group. So, at this point, we have to talk about this in terms of the magnitude. Now, the magnitude of this, if you remember any complex number, a plus bi, if you were to take the magnitude of it, if this is z, then the magnitude is a squared plus b squared under the square root sign, right? So, if you took the magnitude of this or this, it gives you root 2. Both of those would give you root 2. That's why I put them in the same category, because their magnitudes are the same. And I'm going to therefore refer to them as A. Now these guys, these four, in a very similar way, when you take the magnitude, they give the same result. All of them give a half. So I'm going to refer to those guys as B. So that is what we have to work with. Now my product or probability, I think they're calling it product, right? Yeah, not probability. My product is basically this product here of zj from j equals 1 to 12. And they're saying that it's equal to, they want it to be equal to -1. All right, fine. Well, I want to also take the magnitude. If the magnitude is calculated, that's going to help me. And the magnitude of -1, obviously, is 1. So this is the setup of the question. So now let's proceed. Now, in order for us to satisfy this equation right here, we have to basically choose 12 numbers that when you multiply them together, they equal 1. And in particular, the magnitudes equal 1. Okay, well, after you fiddle around with this and think about it, that will happen if you choose 8 A's and 4 B's. Because 8 A's, these are the A's, since each one has a magnitude of 2, root 2, if there's 8 of them, it would be root 2 times root 2 8 times. That's root 2 to the power of 8. And that is 16. If you choose B, 4 B's, it would be 1/2 times 1/2 times 1/2 times 1/2. So basically 1/2 to the power of 4, which is 1 over 16. And then if you took this and multiplied it by that, it would be 16 times 1 over 16, and that is equal to 1. So that is how you would do this. You would get a product of 1 for the magnitudes. So that means we have to choose 8 A's and 4 B's. But the tricky part about this question is that the 4 B's have to be split up. 3 B's are fine the way they are, but 1 B has to be chosen in a special way. It has to be chosen so that this product is negative. That 1 B will be chosen in a way to give it a negative when you're just multiplying the z's, not the magnitudes. So just to recap, we're going to choose 8 A's, 4 B's, 3 B's, and 1 B chosen so that the product is -1 rather than 1 or I or -I. All right, so hopefully that makes sense. So here we go. The probability of choosing an A, this guy, is 2 out of 6, right? Because there are 6 numbers, 1, 2, 3, 4, 5, 6, and there was 2 A's of those 6. So 2 out of 6, the probability of choosing an A. And then the probability of choosing a B, well, if you recall, there was 4 of those guys out of this total 6. So this is a third, and this is 2/3. And the probability of choosing that last B that I was discussing over here, this guy, is 1 out of 6. So I want to show you one such example of how the product can be indeed -1. So for the 8 A's, I will choose root 2 I, and since there's 8 of them, we have b to the power of 8. And then for the other b's, I will choose, there's 4 of them, so I will choose 2 to be the 1 plus I type. So that's going to be to the power of 2. And then for the other 2, I will choose the one that is the -1 minus I. And that's to the power of 2. All right, so here we go. The product. Root 2 to the power of 8 is 2 to the power of 4, which is 16. And then we have I to the power of 8. This 1 over 8 and that 1 over 8, since they're both to the power of 2, are 1/8 each. And when you multiply them, you have 1 over 64. And then now we have to expand this guy, 1 plus I squared. So it's going to be 1 plus 2I plus I squared. And then similarly, we have to expand that guy. And when you expand that, it's 1 plus 2I plus I squared. So 16 over 64 is 1/4. I to the power of 8, I squared is -1. So -1 to the power of 4 will be just 1. And then this should have been an I squared here. I squared is -1, so it cancels with that 1, so you're just left with 2I. And very similarly here, I squared is -1, it cancels with that 1, so you're just left with 2I. So 2 times 2 is 4 over 4, and then I squared is -1. So there we go. We got -1. And that can be done. Here's such an example. All right, so now we have to figure out the probability. Now that I've given you an example, you are convinced that this actually does work. So here we go. Now, the probability of making this from the 12 numbers, remember we're choosing 12, 4 of them have to be B's, right, as stated up here. And the probability of each of those B's is right here, 2 over 3. So 2 over 3. But I'm only going to put 3 because 3 of them are chosen in a way so that you can choose any of them. But 1 has to be chosen in a way so that the product is -1. And that one has a slightly different probability. The regular B's have a probability of 2 over 3rds. Since there's 3 of them, I put a 3. But the special B, that's chosen so that the product is -1 rather than 1I or -I, that B has a product of just 1 over 6. So that's going to be to the power of 1. And then from the remaining 8, you choose all of those 8 to be my A's. These are my 3 B's. This is my last B or special B. And then those A's have a probability of 1/3. So 1/3 to the power of 8. So there we go. That is my probability. So now we have to simplify these numbers. The 12 choose 4 will be 12 times 11 times 10 times 9 divided by 4 times 3 times 2 times 1. And then we have 2 to the power of 3, 3 to the power of 3. Then we have 1 over 6. And then we have 1 over 3 to the power of 8. And then when this is all said and done and you cancel out all the relevant terms, all you're left with is 2 to the power of 2 times 5 times 11 over 3 to the power of 10. 2 to the power of 2, 5, 11, and 3 to the power of 10. That would mean number 25, the answer is E.